station. My team members are Monty and Nick. Today is 420, is the GR328. Outline, I'm going to go over the background, the schematics, the block diagram, and I'm going to go over some previous work, the SSOC, step response, side response, BOD, and root locus, and then I'm going to go over the model, portal, P-only controllers, and the experimental P-only controllers. Then I'm going to go over the proportional integral controller results, and then involved background. Basically what it is, you put in what motor input you want up here for the controller, sends it down to this motor, that turns the gearbox, which allows air to get into this mixer, which runs the plugs that eat waste, and the motor sends a signal up to the transmitter that sends it back to the controller. This is basically like a mini setup of the wastewater treatment plant in Chattanooga, where the whole purpose of it is to give oxygen to aerobic bugs so that you can eat the waste in the water. And there's a 100-to-1 gear ratio on the mixer. Here's a simple block diagram where you have the input motor power, whatever you want to put it in, goes to the aerator mixer system, and an out speed, or its dry speed comes out in revolutions per minute. And here's our SSOC.
Everybody say, boy, that's boring.
Boy, that's boring.
Can you skip down the root locus? That's one of them more interesting.
Boring stuff. All right, here's a sample root locus for the 75 to 95% input region. You have your overdamped region, which is right here, followed by your critical damping point. Here's all your underdamped region, all the way up to the KCU. Here's our root locus results, and this is for the KC values for what's found. That's critical damp, of course, there's KC values of 0. Quarter damp, they range 0.7 to 0.8, and 110 pK, they range 0.6 to 0.7. 1.5 pK, they're all 0.3, and for the KCU, they all had the KCU equal. Here's an example of our P-only model. This is for the KCU response. Here's parameters we did. This is an example run of the highest R base of 1250 RPMs. And then here's an example of the quarter decay at the lowest base. So we ran it to 275. And this is just, again, the model. Here are the parameters, the gain that was run through this system, the tau at that time. And here's an example for the middle range, which was 1,000 RPMs for 1,500 pK. And here are the results from the P-only model. As you can see, they all pretty well match up. Within, they're all within 1 significant figure other than KCU. And that's just within 0.2. Here's the range and the settling time, all again in the relative same vicinity for all the different points, and same for the offset, all kind of around the same ballpark with the 10th K all being the same. Here's the example of the experiment that was run. And again, here the parameters over here on the right. This is run for a quarter decay, or supposed to be a KC value of quarter decay. And here's an example run for what is supposed to be 10th decay, and then another one run for what is supposed to be 500 decay. And here are the results for the experimental values. All again relatively within 1 or 2 decimal points, and then settling times all experimentally wise all in the same ballpark, and same with the offset. Now here is the KC comparison. It's a little hard to read, but every block is modeled right next to the experimental, next to the model for 1,000, which is next to the experimental. Every value lines up so the model agrees with the experimental completely for the KC values. Now here is the settling time comparison, and the critical damping point, the model is just a little bit higher than the experimental, but for the quarter decay, you can see that the model has a lot longer settling time than the experimental has a lot longer settling time than the model, and then for 1/10 there's only a few outliers, and then 1/500 pretty much the same. And as for here, you can see that all the experimental have much higher offsets than the model does for the PLM controller. Here are the parameters used for the proportional integral controllers. The gains for the lower region was 19, the dead time was 0.22, the tau was 0.2, and the tau I was 4. For the 1000 region, gain was 18, dead time was 0.1, tau was 0.11, and tau I was 0.4. And for the 1250 region, the gain was 17.6, dead time 0.18, tau 0.9, and tau I was 1. Here's the root locus for the tau I of 0.4 region with the critical damping at 0.1, 0.01, the 1/500 at 0.04, the 1/10 at 0.09, the critical decay, or the quarter decay, sorry, at 0.1, KCU at 0.2. Here's the same setup for the higher baseline for the tau I of 1, and here's for the lowest one, the tau I of 4. Here's an example of the experimental. This is a quarter decay graph, and here's the parameters. It's run at the middle baseline. And here's the values for the decay ratio. Again, they all pretty much match up across the board with a little bit of variance at the 1/10 decay. Settling time, again, except for critical damping, the 1250 is a little higher. Everything else is pretty much in agreement to one significant figure. And then overshoot, again, is pretty much all the same across the board. And then here's an example of the reset windup, where it goes all the way up to 100% input and then comes down at the step of around. The step comes at 8 seconds, it shoots up, and then it takes about 3 seconds to start heading back down to the input value. And then here's the reset wind down, which is pretty much the exact opposite of what I just described, where it goes all the way down to 0, and then after approximately a little bit over 3 seconds, it comes back up to the input percentage. And in conclusion, the customer gets what they want.